Tim Salez from Université Paris-Dauphine, and he will talk about the recent progress on the cutoff phenomenon.
Okay, thank you. Thank you very much for the invitation. It's a pleasure to be here. So I realize that I'm a bit of an outsider compared to this community. So what I will do is not talk so much about the technical details, and rather just spend the entire talk giving an introduction to this cutoff phenomenon. So as you will see, it's a phase transition in the way in which certain Markov processes, certain stochastic processes converge to equilibrium. But a very important special case is random walks on groups. Okay? And even there, it's completely open to understand this phenomenon. So I hope that you will get interested in that. And you will see spectral gaps appearing in the talk. Okay, so let me describe the setup. I'll consider a state space X which will be finite. So you can think of your favorite finite group. Maybe. And then on this space, I'm going to give myself a stochastic matrix. Okay, it will be my transition matrix. Okay, so this defines a Markov chain, but really, I mean, if you want to think about just simple random walk on your favorite finite Cayley graph, that's totally fine. Okay, the only thing is that it's actually a bit more comfortable to work with continuous time rather than discrete time. Right, so I'm going to consider the heat kernel associated with that, the semi-group, which is generated by this generator L, which is just T minus the identity. Okay, so you know, it's just a complicated way of saying that the probability for my process to move from X to Y in a time T, it's just given by this infinite sum. You do an average over the possible number of iterations, and then you raise your matrix to this power and see where this takes you. Okay, and the main fact about this semi-group is that under milled assumptions, it will be ergodic, it will converge to a unique invariant distribution. So the assumption I need is just that this transition matrix is irreducible. So if you think of random walk on a Cayley graph, you just want your generators to actually generate the group. That's all it means. Okay, so the basic fact, again, is this mixing property that regardless of where you start, if you run your dynamics for a sufficiently long time, you will approach a unique probability measure which is invariant. So phi is invariant under your dynamics. Okay, and so this phenomenon occurs in everyday life. You know, when you shuffle a deck of cards, for example, or when you observe your favorite gas of particles that equilibrate inside a box. It also plays a very important role in modern applications like Monte Carlo Markov chains, where in that case the process is not so much important. The important thing is this probability measure here. You would like to produce samples from it or approximate samples from it. And the most efficient way to do that in practice is to actually find a process that admits pi as the stationary measure and run it for a long time. Okay. So in those examples, it's very important to understand the speed at which this convergence occurs. Okay, so that will be the main question. So can we quantify this convergence? Okay, so if you fix the initial state X, this is just a probability vector on your finite state space. This is also a probability vector, so there are many ways to measure the distance between them. And I'm going to focus on the most natural notion for probabilists or statisticians, which is total variation. Okay, so for me, the distance to equilibrium will be the one given by total variation. So the distance to equilibrium at time t is simply take a maximum over all possible sets in your state space, and you look at the probability that your random process is in this set at time t when it starts from X versus what it is if the process was exactly at equilibrium, and then you take absolute values, and then you take a maximum over all possible initial sets. Okay, so when this quantity is small, your process is really close to equilibrium uniformly in the starting position. Okay. So this function of t has nice properties. So it's decreasing from 1 to 0. from close to 1, say, to 0, in a very continuous way. And it also has this nice submultiplicative property, which simply comes from the semi-group property of Pt, right? Pt plus S is Pt times Ps, and using this, you easily show that the distance satisfies an inequality like that. You just lose a factor 2, but it's not very important. Okay. So this roughly tells you that this function of time is just an exponential. Right. And in particular, you have this subadditivity lemma, which tells you that 1 over t log dtv of t must converge as t tends to infinity. In fact, if you take a minus sign in front, the limit is actually positive. And this is a very well understood parameter. It's the spectral gap of your transition matrix. Or open if you prefer. Okay, so this seems to answer completely this question, at what speed? Right? It means that, if you believe this asymptotic, then this means that, roughly speaking, your distance to equilibrium look like that. It starts near 1, and it's like an exponential. Looks like exponential of minus gamma t. So the time scale on which you should observe the convergence to equilibrium is really 1 over gamma. Okay? So that's the natural time scale for this dynamic. And this seems to be the right answer to the question. Okay, so this quantity has a name. It's called relaxation time. I will explain why in a minute. Okay. And if this was correct, then the talk would be over. Right? That's the end of it. There are many ways to estimate spectral gaps. Therefore, you can understand this parameter on your favorite class of Markov chains, and that should give you the time you should wait before being at equilibrium. Right? So unfortunately, this is not as simple as that. And the reason is this. This exponential approximation is only valid when t is very large, which on this picture means that this behavior is describing something that is roughly here.
Sorry, your matrix is finite?
Yes, the state space is finite. All of this makes sense even later, maybe at the end, if I have time, I will talk about Brownian motions on manifolds. So you can define the same things if you don't like finite state spaces. But yes, in this talk, think of X as being finite. Think of a large Cayley graph. Okay, so this time scale here is really the time scale on which you should look at your function, but once the function is already very close to equilibrium, very close to 0. So it's not really the question that matters in practice, right? If you want to say run your Markov chain or shuffle a deck of cards, the question is really you start from a very well-ordered deck of cards, and you want to understand how long it takes before the distance becomes so small that this exponential behavior becomes valid. Right? So the question is exactly the opposite of what this relaxation time tells you. Right? It's what is this quantity here? Okay. So that's another time scale. It's called the mixing time. There is a parameter epsilon, but it's not so important. Epsilon is simply what you mean by small, but then the mixing time is the time at which your distance becomes small. Okay. So it's just the minimum t, such that your distance becomes smaller. Okay, so that's a much more complicated parameter than this relaxation time. You cannot not reduce that to eigenvalues or anything like that. And that's the quantity we are interested in. Okay, so I described this for a fixed Markov chain, but in fact, this question makes sense and matters really when the size of the state space tends to infinity, so that's what we are going to do. So instead of having a fixed Markov chain, I will have a model which is, for me, just means that your state space is indexed by a size parameter n. Transition matrix is also indexed by n. And what you care about is the mixing time as a function of n. How does this behave as n tends to infinity? Okay. So again, think of random walk, simple random walk on your favorite Cayley graph, except that now the Cayley graph has n vertices and you send n to infinity. Okay, so maybe to make things a bit clear, let me take the time to compute this mixing time on 2 toy models just to see what is going on. So those models are not interesting from a practical point of view, but they are nice in the sense that you can compute everything, and then you can see this cutoff phenomenon occurring. Okay, so the first example, of course, given the audience, I chose Markov chains that are simple random walk on groups. And to keep things simple, the groups are abelian. Right? So the first example is the simplest you could think of, is just simple random walk on the integer model. Okay. So just to formalize, the picture is this. Whenever your clock rings, you make a transition, and a transition is just with probability 1/2, you move clockwise, and with probability 1/2, you move counterclockwise. Right? So you start from 0, n is very large. How long should you wait before this process is roughly uniform on the cycle, uniformly distributed? That's the question. Okay, so by symmetry, starting, so if I denote by xt my stochastic process, the initial state here, there is a maximum over all possible initial state, but in fact, whenever you look at the case of random walk on group, everything is symmetric, so you can just fix this to be the identity, so 0 does not matter. And then you have this simple description that at any time t, because of the abelian property, you just need to count how many times you got this clockwise move and how many times you got this counterclockwise move. And, you don't care about the order in which those appear. So your distribution is completely explicit. Just Poisson distribution with parameter t over 2 for the number of clockwise moves, and then minus another Poisson on a variable independent of the first. Okay. But of course, you are on the cycle, so you take everything model. Okay, so that's as explicit as it can be. And you want to understand this when n is large and t is large as well. And by the central limit theorem, you have a nice Gaussian approximation for this. We know that this is roughly a normal variable with mean 0 and variance t. Right? So if you want this to be roughly of the same order of magnitude as your state space, n, you need to take t to be n squared. So this suggests that the mixing time should be n squared, and indeed this is the case. In fact, you need a bit more than this CLT to conclude this. You need this local version of it. Here this group is so simple that you have explicit Fourier analysis. So you have this local central limit theorem that tells you very precisely the probability that at the time of order n squared, your Markov chain is in a certain state, say nu. This behaves as n tends to infinity, just like 1 over n times ft of u, and this ft of u will be just the density of a Gaussian on a variable mod 1. Okay. So essentially, your random walk on this cycle converges to Brownian motion on a torus, and then that's the density for Brownian motion, and you just wait for this to become uniform. Okay, okay, and from these 4 explicit asymptotics, you do get the expression for the you do get the limiting shape of your distance to equilibrium. Right? Everything depends on n, but if you rescale things by n squared, the graph of your distance to equilibrium, so this graph here, will converge to a limiting function, f of t, which is just how far this is from uniform. So take the L1 norm. Okay, so it's a very nice, smooth, explicit function, almost explicit function. Okay, so if you want to translate this in terms of mixing time, this is the same as saying that the time you need to wait in order for your process to be epsilon mixed is roughly n squared. And if you want to know the prefactor in front, The factor will depend on the precision you want to reach. It's just given by the inverse of this function. Okay, so that's a very precise answer to the question, how long you should need to wait in order for the chain to be close to equilibrium. Okay, but that's not the interesting model for me. I want to talk about the second one, which is again simple random walk on a simple abelian Cayley graph, and this will be the hypercube. -1 plus 1, the n-dimensional Boolean hypercube. Okay, and the dynamics here is very simple. Whenever you have to make a transition, you simply pick one of the coordinates. You have n minus 1 plus 1 coordinates. You pick one of them at random, and you flip it. Very simple. So the transition matrix is simply 1 over n if x and y differ by a single flip, and it's 0, 0. Okay, so again, this is very symmetric, so you can, the initial state does not really matter. So for me, the initial state will just be +1 everywhere. Okay, and the nice thing, this process is so simple that you can explicitate the distribution at any time t. So you will have a vector n coordinates. But those n coordinates, they are actually independent of each other. They are just so IID +1 or -1 with probability. Depends on the number of clock rings that you got, the number of flips of coordinates that you got, and the parity of it, whether it is even or odd. So this is completely explicit. And this is given by this. Okay, so in particular, when t is large, this will disappear. You get 1/2. So you get the uniform distribution on the hypercube, which is the equilibrium measure. And the question is, how should you choose t so that this is close to a uniform measure? Okay, so here again you can do computations. I'll spare it to you, but what you get in the end is again that if you rescale things properly, you will see a limiting profile. Now the correct scaling to see something non-trivial is n log n. Right? So you rescale time by n log n, and you send n to infinity, and then you get a limiting profile as before, f of t. But now f of t is very degenerate. It's 1 or 0. So it's 1 if t is less than 1/4, and after that it's 0. Okay, so that's a very surprising convergence to equilibrium. It's not at all like we had before. Right? So now you run your Markov chain, and essentially nothing happens for a very long time. You remain as far as you can be from equilibrium. So being at distance 1 means that your Markov chain actually lives on a set that has measured almost 0 compared to equilibrium. And then suddenly you reach this particular time, so 1/4 n log n. And then at this time your process is at equilibrium. Okay. Of course, that's a limiting description. Right? That's what happens when n is infinite. So for finite n, you will see something like that. So that's a phase transition in the way in which this Markov chain converges to equilibrium as opposed to that one. Right? And this is what the cutoff phenomenon is about. So that's a cutoff. I will give a formal definition later. And that's really what I want to describe today. Okay, so before going to the general definition, let me observe that you can translate this in terms of mixing time. So what does it mean in terms of the time you need to wait for your Markov chain to be mixed? Well, you see in this picture here, you choose your precision epsilon, and the time is always 1/4 n log n, regardless of epsilon. Okay, so the fact that you see a phase transition, a step function like that, is translated when you look at mixing times, which are the inverse of those functions. It's translated into the fact that this mixing time becomes independent of epsilon as n tends to infinity. Okay. So that will be my definition of cutoff. Yes? So maybe I should not use this board. No, I'm going to do it right now. This was just an example, and now we can move to the general definition, but it's exactly what you saw. Okay, so the definition is due to David Aldous and Paris-Dauphine. The phenomenon was discovered more than 40 years ago. On card shuffling, we'll come back to that. Okay, so you say that a model, so remember a model is just a sequence of Markov chain, right, indexed by n. Exhibits cutoff. If the distance to equilibrium, once you rescale it properly, converges to a step function. Right? So in terms of mixing time, you're just saying that the mixing time becomes asymptotically independent of epsilon. It takes the same amount of time to start mixing or to be completely mixed. Okay, so that's an example of a cutoff, and that's an example of where there is no cutoff. Is the definition clear? Okay, so I just told you that this phenomenon was discovered in the context of card shuffling. You know, you take your deck of 52 cards, and there are several ways to shuffle it. I didn't take my own deck, but the most canonical one is to just split the deck randomly into two halves and recombining those two halves at random. You see what I mean? Okay, so if you do that, then there is a cutoff. I mean, what is n here? It's the number of cards. And you know, when n is large, there is a cutoff. The time at which you should you converge to equilibrium is around 3/2 n log n, 3/2 log n, sorry. And when you compute this for n equals 52, you get something like 8. So it tells you that you should shuffle your deck of cards at least eight times, and actually not much more than that, because otherwise you are wasting your time. Okay? So Paris-Dauphine discovered this in the 80s. And you know, he realized that people in casinos were not shuffling the decks enough. They were shuffling it like five times. So if you are not at all mixed, if you are before the setting point here, it means that your distance is very close to 1. So it means that there is an event, there is a region of your state space where your deck is actually very likely to be, almost probability 1 to be, whereas if the deck was uniform, was really uniformly distributed, then the probability will be 0, or very close to 0. So you can bet on this event, and the casino will agree to bet on it because it's very unlikely that this happens, and you will gain a lot of money. So that's what Percy did. It's a true story, I asked, and he confirmed. And then he got kicked out of the casinos because you are not allowed to do that. Right? You are not allowed to think anyway. So he got even blacklisted from all casinos in the US. But then he got recruited by a company that devises shuffling machines. And you know, thanks to him now, if you go to casinos, you'll see that the decks are properly mixed, like at least 8 or 9 times. It's really uniform. Okay, so that's, you know, there are many ways to shuffle cards, and for some of them we can do computations and check that indeed there is cutoff. So that's a large class of models. More generally, card shuffling is just a particular case of random walk on a group. Right? So again, you can take your favorite finite group, your favorite probability measure whose support generates the group, and then what you do is at each time you multiply your current position by a random element drawn according to this distribution. So that's a random walk on a group. A special case is of course Cayley-Glass, but this is more general. And again, if your group is simple enough, so you see 2 examples here of abelian groups where you can do computation. The group is simple enough, you can do computation and check that for many of them there is cutoff. Okay. There are many other contexts where cutoff has been proved, but those are probably less interesting to this audience. But, you know, look at your favorite model of interacting particles on a graph. You can also look at Monte Carlo Markov chains. And maybe relevant to this audience is Brownian motion on your favorite compact manifold. And, can ask the same question. And again, if the manifold is simple enough, say the sphere, a high-dimensional sphere, then Brownian motion will exhibit cutoff. We can do computations and check. Okay, so this looks like a very wide list. There are now more than 100 examples of models for which cutoff has been proved. So that's nice. But there is bad news as well. And the bad news is that all those proofs, they are very model-specific and very much based on the exact computation. Okay, so just to explain why this is bad, I mean, the first bad news is that those computations, you have to do very precise computations. I will explain why. And this is only doable for very simple models, like the two I have presented. And so there are many models for which we expect a cutoff to occur, but we cannot prove it because we can't compute things. Okay, that's the first thing. The second annoying thing with this approach is that you don't understand the phenomenon really. What you understand, you do the computation and you just check that in the limit there is a step function, but you don't see why there is a phase transition in this example and not in this one. What's the reason behind that? Is not clear. Okay. Okay. So how do you prove cutoff so far? You just open your favorite book on mixing times, and the theory of mixing time is really a collection of upper bounds and lower bounds. You have techniques to bound the mixing time from below and from above, using very different things. You can use the spectral gap. You can use the information on other eigenvalues and eigenvectors. You can use the geometry of your state space, notions like curvature, things like that. You can use coupling. It's a very rich theory, very nice theory. And if you apply this theory to your particular model, the one for which you want to prove cutoff, so you will have to find a good upper bound, a good lower bound. And by good, you are already very lucky if those lower bounds and upper bounds, they are of the same order of magnitude. Because then you can claim, random walk on the cycle takes roughly n squared steps to mix. Okay, so that's good. But if you want to understand cutoff, you need much more than that. Not only you need the order of magnitude to be the same, but you need to know the prefactor. And the prefactor here has to be the same as there, so that you can check that it does not depend on epsilon. Okay? And this is much more delicate to do. This is restricted to a handful of models where you can do very precise explicit computation. Okay, so that's a limit of the model, in a sense. And so what Aldous and Diaconis asks for, when they discover this phenomenon, is a theory that is able to predict cutoff without doing computation. Okay, so that's the question I'm going to be interested in. But again, it's due to the master. So, can we predict cutoff? Without going through this brute force computation, right? Without computing this quantity, this T mix of epsilon, up to the prefactor itself. And this is still wide open, even when you restrict yourself to random walk on Cayley graphs of abelian groups. Okay, so cannot be simpler than that, but still it's annoying. We don't understand cutoff even on abelian Cayley graphs. Okay, so it's probably not clear to you what we could expect, what kind of criterion could be an answer to this. There has been a famous attempt to solve this question, and I want to describe that now. It's called the product condition. So 20 years ago, there was a workshop, an AIM workshop on mixing times, where this question was raised again. And Yuval Perez was there, and he proposed the following answer. Conjecture. If you want to know whether a model exhibits cutoff or not, all you have to do is understand the spectral gap of this model and the mixing time, but just the order of magnitude. So his proposed answer was the following: that you see a cutoff if and only if the mixing time, and I don't need to tell you the precision, I will explain why. The mixing times the spectral gap, which depends on n as well, tends to infinity with n. Okay? So you see here, I don't really care about the prefactors, right? It's really something about order of magnitude. I just want this to be large. I don't care about the prefactor. And that's why I don't need to tell you what epsilon is here. Because when you change epsilon, you just change the prefactor. Take whatever epsilon you want. And this should be equivalent to cutoff. It's a very nice condition in the sense that it's effective. Right? There are many, many models for which we can check this. You have many estimates on the spectral gaps. You need a lower bound on the mixing time, but a rough lower bound, you don't care about prefactors, and lower bounds are much easier to obtain than upper bounds anyway. So this is really something that you can check easily on models. And there are thousands of models for which we know this. Okay, so that's effective, that's nice. The second good news is that if you check this criterion on our two models, it's actually an explanation for cutoff or not, so it's correct on those two models. Right? So if you ask, what's the difference between those two random walks, you don't see it from the point of view of mixing times, but when you compute the spectral gap, all the eigenvalues are explicit in both models. You'll see that the spectral gap here is also n squared, like the mixing time. Whereas here it's n, and the mixing time is n log n. Right? So that could be the right explanation for cutoff. Okay, there is another good news, which is that one of those two directions is always correct. The conjecture is the equivalence, but at least there is an implication which is known. And it's this one. Okay, so this implication. So if you want your model to have cutoff, then the product condition has to be satisfied. So in particular, if you come back to those two toy models, here, just a simple computation of the spectral gap will tell you that there is no cutoff. Unfortunately, the other direction, which is the one that would really answer this question, fails. Okay, so I mentioned this workshop, this AIM workshop where this conjecture was proposed. So David Aldous was in the audience, and apparently half an hour after he produced a counterexample. It's a very sophisticated one, so Yuval did not like it. And Yuval said that this was not reasonable. It was not an acceptable counterexample because it's too pathological. Okay, so he changed his conjecture. He said, okay, this, but for reasonable chains. Okay, and unfortunately, it's still, even with this correction, it's still wrong. It's really, the guy is crying. It's in fact, counterexamples are everywhere. I'm going to explain that, but it's really not a pathological thing. Okay, so what do I mean by this? You give me your favorite model that satisfies cutoff. So in particular, it satisfies this product condition. And then I can perturb it in a very tiny way, and I will destroy cutoff, but this will still be preserved. So in this way, I can create counterexamples near every model. And the transformation is very simple. This perturbation is the following. So you give me a transition matrix, and I'm going to change it as follows. So this is my perturbed model. Most of the time, I'm going to do transition according to the original rule. But from time to time, with a probability theta, which will be very small, which tends to 0, I will allow myself to jump directly to equilibrium. Okay? So it's a rank 1 perturbation of my transition matrix. Right? And again, everything depends on n. I have a model where everything is indexed by n, and I'm going to choose theta that tends to 0 with n in a particular way. I want it to be small, but not too small. I'm going to take it smaller than the relaxation time, so 1 over the spectral gap, but larger than the mixing time. And so the opposite. That was correct. Larger than 1 over t. Okay, so you can always choose a theta like that because you started from a model that satisfies cutoff. So in particular, it satisfies this. So you have plenty of room between those two numbers to stick a theta n in between. Okay, and if you do that, the product condition remains valid, but cutoff is destroyed completely. In the limit, you get convergence to a nice exponential profile. Okay. So this simple perturbation destroys cutoff.
The right-hand side is gamma.
It's gamma, you're right. Thanks. Okay, so the conclusion of this is that cutoff is very subtle. It's something that you cannot really understand by a simple condition like this product condition. No, those two models, this one and this one, they are very close to each other. And this is not true only in terms of entries of the matrix. Right? Theta is very small, so those entries are very close. But even in terms of structure, right? For example, if you want to look at the eigenvalues and eigenvectors, the eigenvectors are actually exactly the same for T and T tilde. The eigenvalues are a very simple shift, so completely trivial transformation. So this means, and yet, this one satisfies cutoff, this one doesn't. So it means that cutoff is something that you cannot reduce to eigenvectors or multiplicities or things like that. It has to do, you have to understand the matrix in a very precise way in order to distinguish this from this. So if you want to repair this product condition, you will have to find a way to find a criterion that distinguishes between those two models. Okay. So in particular, if you look at random walk on your favorite group, right? So this means that this is just you choose a generating measure, and then this transition matrix is simply the probability to pick the right generator that will move you from x to y. So y x inverse. And this transformation is still of this form. You just have to add a bit of the identity here. But it's still a random walk on a group, and on the same group. So it means that you will be able to construct counterexample to the conjecture of Duval, even on abelian groups, or any group you would like. Okay? That's why I'm saying that this cutoff is still not understood even for abelian random groups. Okay, still, so if you want, so that was the negative part of the talk, but there is one hope, because there is one property, those two matrices, they are very close to each other in many, many ways, but there is one crucial difference between the two models. This one could be a random walk on a bounded degree graph, so it's a local, think of this as being a local random walk where you only move to neighbors. The big difference is that this one here is always fully connected. You can move, you have a positive probability to move from anywhere to anywhere in your Cayley graph. Right? So this is a pathology, and somehow you should take this sparsity into account here if you want to repair this condition. Okay. Okay, so I have a bit of time to talk about positive results now. So on how to repair this product condition of Duval. Using an information theoretical statistic called varentropy. Okay, so when I started working on this problem of cutoff, so I realized one stupid thing, which is that what is difficult in proving cutoff is that you really want to understand, you try to understand this up to a precision 1 plus theta log 1. So that you determine whether this depends on epsilon or not at some point. But this is too difficult to do in general. And in fact, if you want to understand whether a cutoff occurs or not, this is not the thing you should be looking at. You don't want to know where the transition will appear here. You just want to understand whether the transition will be sharp or not sharp. So it's not really this that you want to understand. It's the difference between the final time and the initial time of the mixing. So the key quantity is a difference of mixing time and not the mixing time itself. Okay, so let me define this mixing window, which is the difference between being completely mixed and being barely mixed. Think of epsilon being very small. Okay. So the cutoff is really saying that this is small. Okay. And so maybe the hope is that if you want to understand cutoff without computing this, maybe you should look for a way to estimate this difference without estimating each of the two terms separately. So it's not clear that this is possible, but this might be the key. Okay, so it turns out that there is an estimate on this mixing window that does not involve computing each of those two terms separately. And this estimate requires this var entropy, this mysterious quantity. So let me define this for you. So, but before going to the definition of var entropy, maybe let me recall what is familiar to everyone here, maybe, which is entropy. So what is entropy in this context? I described the total variation distance to equilibrium. There are other ways to measure the distance to equilibrium, and one of the most important one is the relative entropy. So the entropy of a probability distribution on the state space with respect to your stationary distribution is simply this integral. I think it has an integral, but it's really a finite sum. F log f d pi, where f is your the density of mu with respect to pi. This is well defined because I'm on a finite state space. Okay, so that's the general definition of entropy. And I'm going to write it in a slightly different way. I'm going to view this as an expectation. This is really the expectation of log f under the measure mu. Right? So it's expectation under mu. It's an average under the measure mu of log of this function f. Okay, it's just a way to interpret this integral. But now that I see this expectation, I can do the following. So maybe before that, this entropy is, by Pinsker's inequality, it's always an upper bound on the total variation distance. And it's a quantity that is much better behaved in many ways than total variation. So a good way to obtain upper bound on mixing time is to actually replace total variation by this larger quantity and try to estimate how this evolves in time under your semi-group. That's the entire idea behind modified log-Sobolev inequalities and log-Sobolev inequalities, which are very powerful tools to get upper bound on mixing times. Unfortunately, you will get constant here that will be different here and there, and so you won't be able to prove cutoff using that. But if you are interested in mixing times up to prefactors, then this is a very powerful quantity to look at. Okay, so here we are not focused so much on mixing times themselves, but on differences of mixing times. So instead of looking at entropy, I'm going to look at a second order version of entropy, just replacing expectation here by variance. So that's var entropy. The var entropy of mu with respect to pi is simply the variance corresponding to this expectation. Okay, so if you want it, integral of f of square of f d pi minus integral of f log f d pi squared. Second order version of entropy. It has nice properties. It was introduced in coding theory because, in coding theory, this entropy plays a significant role. It's, the rate at which you can transmit symbols without loss, optimal rate. And behind is there is a strong law of large number, or the asymptotic equipartition property, which says that basically the log of the probability of observing the symbol that you observe will converge to this entropy. And if you want to control the error in this asymptotic equipartition property, you need to look at the variance, and it's exactly this quantity. Okay, so this is a natural quantity in coding theory, but in Markov chain it has not been used at all. And my claim is that this is the right quantity to look at if you want to understand cutoff. Okay, so here is the justification for that. So it's completely universal. You take any Markov chain. This was a couple of years ago. And you want to estimate this mixing window, the quantity that you want to estimate without having to estimate each of the two terms separately. And you can estimate it using var entropy, so it's at most a constant times 1 over the spectral gap, this important parameter, times 1 plus square root of this var entropy. What is this var entropy here? maybe I'm going to write it like that. V epsilon. And what is V epsilon? It's the varentropy of your Markov chain at the mixing time. Okay, so V epsilon is simply you take a maximum over all initial state, but this is just because you want to understand mixing starting from the worst possible condition. And then you look at this varentropy of your distribution at time t starting from x compared to equilibrium. And the time that you look at here is the mixing time. Okay, so it looks like a complicated quantity. Right? Okay, maybe I have an estimate on this mixing window, but how efficient is this? Can you really compute this without computing mixing time? So my claim is that this is indeed the case. You can. I will try to convince you of that. But really, the corollary that is important here, if you come back to the definition of a cutoff, right? The cutoff means that this is small. So using this estimate, you get cutoff. As soon as the product of gamma and the mixing time, everything depends on n, but I'm not going to write n explicitly anymore, is larger as n tends to infinity than this parameter, 1 plus square root of this. Okay? You want this to be true for every precision epsilon. Okay, so just a comment, if you remove this, that's the product condition of Yuval. And we know that this is not sufficient for cutoff. So what this theorem tells you is that if you want to repair the product condition of Yuval, all you need to do is add this correction, this varentropy correction. But again, I mean, at this point, you should not be very happy, right? Because this is a complicated quantity. It's probably much harder to compute this, maybe, than to actually compute mixing times up to the precision 1 plus beta of 1. So it's not clear that we have gained. I need to convince you of that. Okay? Huh?
You know to be optimal.
I know it to be optimal, at least for expanders and a more general class than that. And expanders would already be, I mean, it's probably the most important class of examples. Yes, I was planning to write this here, but then I gave up. Okay. So just a quick remark before I convince you that this is actually, this varentropy can be estimated on interesting models. Let me go back to our toy model, this hypercube. Remember that so far the product condition of Yuval fails even on abelian Cayley graph. So in particular, you cannot deduce from the product condition that you do have cutoff in this simple toy model. But you know, varentropy is a nice quantity in the sense that if you look at product measure, you have a nice tensorization property. You compute the varentropy between a product measure and another one. Just like entropy, this will tensorize, so this will be the sum of the individual varentropy. It's easy to deduce from the definition. And in particular, you know, if you look at random walk on our toy model, the hypercube, the coordinates were independent of each other. So in particular, for the hypercube, you can compute this varentropy explicitly because it will be n times the same thing, which is the varentropy of the first coordinate. It's just a +1, -1 random variable. You know the parameters explicitly. You can compute things. And you can check that this varentropy correction depends on n, but in fact is of order 1, remains of order 1 as n tends to infinity. Which means, retrospectively, that this product condition of Yuval was actually sufficient to imply cutoff on this example. Okay? But you need the varentropy computation to make sure of it. Okay, and you know, this also gives you a potential answer to this repaired conjecture of Yuval. You know, what's the meaning of reasonable? Maybe reasonable means chains for which you have this. Okay, so now let me move forward and tell you a bit of what. So this result tells you that if you want to understand cutoff, the right thing to do maybe is to try to estimate var entropy. So can we now develop systematic tools to estimate var entropy, just like it has been done for entropy? Okay. Can we define like log Sobolev inequalities or things like that, but for var entropy?
So, question. So this theorem and conjecture also, it's, you only stay on finite graphs? Or?
Yes, finite, but the size tends to infinity. Again, you can also make sense of this on manifolds if you want, then it's infinite. But you have to have a parameter that tends to infinity, maybe the dimension of your manifold. Or it's an asymptotic because for finite, for a fixed process, this distance to equilibrium, this graph is continuous. So if you want to observe a phase transition, you have to send something to infinity. Okay, so to turn this into an effective theory, I need an assumption on the Markov chain, and this is curvature. So I want to talk a bit about curvature. So I'm not a geometer, as you can tell, but the picture that I have in mind when I hear the word curvature is this Ricci curvature. I know that Riemannian manifolds can be classified according to this important parameter. And that's the picture that I have in mind. Maybe it's not very correct, but that's roughly what I have in mind when I hear the word curvature. So Ricci curvature is a very important parameter when you study Riemannian manifolds. The knowledge of this gives you a lot of properties on your manifold. And this theory is so powerful that people have recently tried to make sense of this notion on discrete spaces, in particular on Markov chains. So there are ways to define a curvature similar to this picture, but for Markov chains. There are actually several ways to do that, and they are not equivalent to each other. So today I'm going to focus on this Bakry-Henry curvature. Okay? And what I want to convince you of is that the cutoff phenomenon, or at least this var entropy, and therefore the cutoff phenomenon, can be understood and is now understood roughly in this world. So there, we have a pretty decent understanding of a criterion for cutoff, and that's what I'm going to discuss. But in this case, I don't know how to estimate var entropy, so this is work for you. So this case is important because it contains random walk on expanders. So there is a huge conjecture in the domain, which is that you take your favorite sequence of Cayley graphs that are expanders, so the number of generators is fixed, the size of the group tends to infinity, and you want the spectral gap to be bounded away from zero. The conjecture is that there is cutoff. The product condition of Yuval is satisfied in this case, trivially. There should be cutoff. The only examples for which we know how to prove that, explicit examples, are Ramanujan graphs, or almost Ramanujan graphs, because there you can do computations. So this has been proved using spectral techniques by Yuval Perez and Eyal Lubetsky. But there are now several other proofs, and there is one by Narutaka using entropy. Okay, so it's a case. Ramanujan graphs are a special case of expanders for which we know how to compute things and for which we know how to prove cutoff, but it's wide open to move beyond Ramanujan graph, and it should be true for any sequence of expanders. Cayley graphs or vertex transitive expanders. Okay? So that's work for you. I'm just going to focus on this case where I know how to estimate this var entropy. Okay, so there are several notions of curvature. The one I'm going to use is the Bakry-Henry. It's a bit delicate to define it.
Just in the case of Ramanujan graph, you also have a proof using var entropy? Can you reproduce this using var entropy?
Yes, but in this case, yeah. Anyway, I have a result that says that for any expanders, the var entropy criterion is sharp. So if you know that there is cutoff, then the var entropy, there is a var entropy proof just by definition. But so now you can reinterpret all the works on the Ramanujan graphs using var entropy, and it works very well. But it's really about going through the exact computations, which is not what we should do.
And you're saying the var entropy was already hidden in those proofs?
Not in the first one, but in the second one, the one of Tanaka, yes. You can reinterpret all those, this cutoff has been first discovered on random graphs. And there it's very clear, if you look at the proof, it's not written in this way, but it's very clear that what matters is the concentration of log of pt around the mean, so you can formulate it. A posteriori, it's always easy to say that. But viewing it as a variance is very important for what I'm going to say now. Okay, so what is Bakri-Emery curvature? It's a bit delicate if you have never seen that. But there is a way to define curvature for any Markov process using the carré du champ operator. Okay, so this curvature is the largest number kappa, such that you can interchange the semi-group and the carré du champ operator. I'm going to say what this is. By paying a cost which is exponential with rate k for everything. Okay. So those are operators on are operating on function of my state space. So this inequality is really an equality when you apply it to every function on the state space. Right. So PT is just the semi-group operator, the Markov semi-group, but gamma is this quadratic operator, the carré du champ. It's just, you know, how much f varies when you do a transition starting from x. Okay, so you look at this variation in the quadratic sense, and that's gamma. Okay, so it's this mysterious property. Looks very complicated, but in fact, we know how to compute curvature for many examples, and it's non-negative for many examples. Okay, so shades which have k non-negative are very nice. Essentially, people have been playing this game of trying to reproduce all the nice results about Ricci curvature of manifold, trying to see if those hold when you replace manifold by a Markov chain and use this definition of curvature. And many of those results have analogs. The story is not as simple as in the manifold case, but still you can deduce a lot of nice things. You have spectral gap estimates, just like the Lichner-Horowitz estimate for manifold. There is an analog of that here. You can take every basic result in Riemannian geometry and try to find an analog there. Okay, and there are many chains that have these properties. And those include the random walks on abelian group. So every random walk on an abelian group has this k being non-negative. More generally, any conjugacy invariant random walk. When the set of generator is a conjugacy class. So for example, transposition random walk on the symmetric group. And also, if you are interested in Monte Carlo Markov chain, there are a lot of nice algorithms. When you want to sample from a nice product near product measure. Okay, so there is a huge class of examples, interesting examples for which we know that this curvature is non-negative. Okay, so what I want to tell you is why this is interesting for cutoff. And the reason is that there is a nice reformulation of it's an implication, but in fact you can see it as an equivalent way of rephrasing this.
Excuse me.
Yes.
Do we have this for k strictly larger than 0?
Yes, I mean, so I will only need this. I don't need a precise value for k, but yes, if, you know, for example, for the toy model, the hypercube, k is 1/n. I mean, you have results like that. Yes, for Monte Carlo Markov chain, if your measure is close to a product measure in a quantitative sense, then you have a quantitative moment on how positive k is.
But it has to 0?
Yes, it has to.
Okay.
Yes. It has to when the diameter of the state space tends to infinity, k has to tend to 0. Okay, but I will only need k to be non-negative. So the reason why k is interesting for us is that it gives you local Poincaré inequality. So it gives you a way to compute local spectral gap. So what is a local spectral gap? So this number, this k parameter, shows up in this inequality that if you want to compute the variance of any function of your Markov chain at any time, it's a very general statement, then you can estimate this global variance, if you will, in terms of local variation of f, just like a usual Poincaré inequality. So there is a constant t which depends on t and on the curvature. And then local gradient, if you wish, which is just this gamma operator. So local variation of F evaluated at X. Okay, so that's a local Poincare inequality. It's called the Poincare inequality. Again, if you send t to infinity here, this will converge to the uniform, the stationary measure. So this is really the variance under the stationary measure. And this is the Dirichlet form of your process when t tends to infinity. Right? So it's really the usual Poincare inequality, the one that controls the spectral gap. The word local here means that you have a Poincare inequality, but not under the stationary measure, under the measure, under your random walk at any time t. Right? You have an understanding on how this evolves with t. So this is explicit, is an explicit function, it's simply this. Okay, so in particular, when k is non-negative, this is just t. Okay, so you get this nice ways of estimating variances by just understanding local variations. Okay, and why is it interesting? Because varentropy is a variance. You can just plug this formula and try to see what it gives. Yes?
So we're over time.
Okay. So yes, I think that's a good point to stop. Again, major open problem is try to estimate varentropy for expanders and prove that there is cutoff on expanders. It's a super fancy conjecture.
We have time maybe for one quick question.
But we want to see the positive result.
No, it's good. I mean, we can keep it for the coffee break maybe.
So quick question. So for these expanders, if you don't know that they are Ramanujan, but you know large girth, is it better?
No, you would need the girth to be optimal, to be Ramanujan-like, which is really, you want a precise constant. Not only you want it to be of order the diameter, but you want the constant to be the optimal one, the one for Ramanujan. And then you can have a proof. But it's, again, it's really annoying. It's about computing things. Just like I did on the toy example, it's not really about understanding the phenomenon.
Okay, let's then just again.